Okay, hello again. My name is Devin Cairns. This is the last video in the video series going over how to represent subsurface carbon reactions in the watershed scale reactive transport model BioRT-HBV. And this is video 4, and we're going to go over how to implement kinetically controlled sorption processes into BioRT-HBV. The previous video was implementing sorption processes via an equilibrium controlled reaction. And so we'll set up this reaction in BioRT-HBV and compare it to the equilibrium controlled reaction and kind of talk about why we may set up these different reactions in our watershed scale reactive transport model. Let me do full screen this. Okay, so we implement, again, our sorption processes in this shallow soil zone. Yep, so similar thing as the last video where we implement it in our shallow soil zone and on top of our shallow zone and deep zone respiration processes, reactions that we've built into our model. So in terms of the reaction equation, we represent this by a really simple reaction equation where we have DOC sorbed to the solid phase, which is represented by this X. And as it dissolves or releases from the solid phase, we get DOC in the aqueous phase. So the kinetic reaction rate law for sorption, we follow transition state theory when we implement this into BioRT-HBV. And so this is so that we can represent sorption processes with dependency on temperature, soil moisture, and water table depth. As often we find most DOC may be sorbed in the shallow soils or maybe higher up in the hill slope, which would require your system to wet up before you start releasing this DOC from the sorbed phase. So we can really implement that dependency on moisture and climate and connectivity of this watershed, even though BioRT-HBV in terms of this is defined as a 1-grid model. If we implement these soil moisture sensitivity functions, we can really account for this watershed hydrologic connectivity and the release of DOC when the water table wets up into that more into that shallow soil phase where more DOC is stored onto the soil phase. And so when we get that water flowing through, it can actually start to flush out. So again, it's very similar to our Monod rate law, except we have this term that incorporates the saturation index of our saturation index, which is dependent on the equilibrium of the system. And so the equilibrium of free DOC to stored DOC. And again, how we implement this and what input files we amend are similar to the input files we amended for each of the previous videos. Our chem.txt file, double checking our database, setting our initial conditions, and making sure our chemistry or our precipitation chemistry time series are updated. So in terms, make sure our reactions are turned on, and we will need to list our primary species. And again, if we look, this is a kinetically controlled reaction. And so we're considering this our solid phase, which our solid phase is just our DOC, represents our DOC, which is already stored to our soils. So we list that as our solid phase, so XDOC solid. We also need to tell it where to look within our database. So again, we'll list our XDOC solid. We'll have our label. It's misspelled. I love these types of videos because you can totally see the types of mistakes I make when I set these all up. So obviously if you misspell something, it won't run, but you'll see when we look at the actual input files I've set up to run this process, it'll be spelled right. So these are the types of mistakes you make when you set these things up. They happen all the time. So just types of things to look for. That's why I've made these mistakes, is so you know what to look for. Okay, so we'll double check everything in our database again. So we'll have our primary species. we'll check our reaction network here, which we've added our sorption reaction network. So we'll check that that's in the database. Then we'll also check the kinetics block. So we can see XDOC in the kinetic block here. It's controlled by a transition state theory. You can see that the label is default, and we see that our chem.txt file, the label is default. So it will tell the model to look at this block in the database. And then we will set up our initial conditions. And again, just because the only thing we already have DOC listed as a primary species from our previous reactions, the only line we will add is this XDOC solid phase. And all these different, again, you'll set the volume fraction, specific surface area, and the reaction rate parameters themselves. And last but not least, we will set, again, best practice order is we'll have our aqueous species, pH, carbon dioxide, DOC, and then our solid phase species, which is our organic carbon in the shallow zone, organic carbon in the deep zone, and then this XDOC. Oh, okay. So now let's look at really quickly how we set this up in our input files. So we'll go to Sleepers River Kinetic Sorption, which I've already set up. We'll look in our chem.txt file. We can see that we've added XDOC as a primary species and XDOC down here. Fix the label, the default. I just like these all to line up sometimes. Then we'll check, our database, check our reaction networks. So XDOC, we have it here, XDOC solid, make sure that it matches here, XDOC solid. Then we'll look for our kinetic block, label default, okay, all looks good. We'll look at our initial condition file. We can see that in each of these zones, I've added a line to represent our new solid phase we have added. And again, because most of the sorption processes we're trying to account for are happening in the shallower soils due to the more available sorption sites of the shallow soils. We've set that to an initial volume fraction and specific surface area. And in the deeper zone, we've actually set a very small volume fraction and a very small specific surface area to represent less of these sorption processes happening in these deeper groundwaters. And last but not least, we'll check our precipitation chemistry files. And as you can see here, we've done best practice order, our aqueous species first, and then our solid phases at the end. And so now we can run this with Sleepers River Kinetic Sor. So again, we've just typed in /BioRT, Sleepers River, and then we'll change this to Kinetic Sorp, double check that it. Gosh, I am a terrible speller. Please do not judge me. Kinetic Sorp, okay. Nice, it ran, we did it. Okay, so now we will check the output of this. Which I've already plotted. So here we have the results. And so on the left here is where we've implemented equilibrium sorption. And on the right here is where we've implemented kinetic sorption. And so we can see the decrease in concentration of DOC as well as the decrease in concentration of DIC. And so that's really representing the fact that we're having much more sorbed and much less released in the system. And so when we compare these to each other, we can see that when we implement the kinetically controlled sorption, we get a much bigger decrease in DOC concentrations. We get a decrease in DOC concentrations in the deeper zone as well, because we have less DOC in the shallow zone in the aqueous phase, so we have less percolating down into the deeper zone. So that's where we can really start to see why we have this lower concentration in the deeper zone. In the upper zone, we have lower concentrations of DOC. And this is really representing the fact that when we have implemented this dependency on soil moisture we need to have really wet states in our catchment to release this DOC. So what's happening here is our catchment isn't actually getting wet enough to start releasing this DOC. So we actually see the produced DOC ends up being sorbed to the solid phase more and less is released into the aqueous phase. And so why we would implement kinetically controlled versus equilibrium controlled can represent the sensitivity of sorption processes to a catchment wetting up or not wetting up in hydrologic connectivity. So the way I've been thinking about it is when we implement these equilibrium controlled reactions, they are highly responsive to stream flow and happen really fast. If you have a small change in subsurface storage of water, when your concentration changes, you'll get a response in the amount of DOC sorbed or desorbed to the solid phase instantly. And so to me, this represents, if you have even a small change in water, it would represent the areas of DOC that contribute to your stream tend to be hydrologically closer to your stream. So it only takes small changes in water to see that sorption response of DOC. However, when you have these DOC stored in more hydrologically distant parts of the catchment, you need to make sure that you can allow for a much bigger wet up of your catchment before your sorption processes start to respond. And when we have a one grid model, the way we can do that is implementing our soil moisture dependency functions in our reaction rate law. And so when we've implemented these kinetically controlled reactions, again, we're really accounting for, we need a lot of increase in water to really wet up these catchment and connect these hydrologically distant sources in the catchment that may have DOC sorbed to the soils. And so you don't start to see that DOC from desorption contributing to your groundwater or your stream DOC concentrations until you get that really wet state, which is where you can start to see these increases in DOC happening, as they tend to happen at the times of highest flow. And so thank you for watching all these videos so far. My email is dkaren01@hotmail.com if you have any questions or any questions further on BioRT-HBV. You can always email Dr. Lee, who's the head of Lee Reactive Water here at Penn State at lxl35@psu.edu. And again, this is part of a larger series of videos of implementing many different reactions in BioRT-HBV. So just to emphasize, this model could do a lot of different reactions, so I would definitely recommend watching some of the other videos to really get an understanding of the breadth of application of BioRT-HBV. Thank you very much. Hope you have a wonderful day or evening, depending on when you're watching this video.